You know that feeling when you have more information than ever before, but somehow you feel less sure about what's going to happen? Well, today we're diving headfirst into a really fascinating puzzle in the world of data, the predictor's paradox. It's this strange idea that adding more clues to the mix can sometimes make the picture much, much fuzzier.
So let's ground this in something we can all relate to. Imagine you have to predict the price of an apartment. It's a complex problem, right? Where do you even start?
Well, a simple model is a great place to begin. You'd probably look at the most obvious thing, its size. Square footage. It's a solid logical first step. I mean, a bigger apartment should cost more. Simple enough.
And it just makes sense that adding more good information should make our prediction even better. So we throw in the number of bedrooms, maybe the number of parking spots. Each new clue should bring us one step closer to nailing that price.
Okay, but this is exactly where things get weird. Because sometimes adding more perfectly good information doesn't just not help. It can actually make our model completely fall apart in a really surprising way.
So to handle all these different clues at once, we've got to upgrade our toolkit. Let's take a look at how we go from a simple one-clue model to something way more sophisticated.
And that tool is called multiple linear regression, or MLR for short. Just think of it as a way to weigh the importance of a bunch of different factors all at the same time. It's pretty much the go-to method for any data scientist who's trying to predict a single outcome, like our apartment price, from a whole host of different variables.
And right here, this is the absolute heart of the paradox. A predictor's power can be measured in two totally different ways. When a variable like square footage is a lone wolf, acting all on its own, its impact is clear as day. But put it on a team with other predictors, and now we're only measuring its unique contribution, what it adds after everyone else on the team has already had their say. And that changes everything.
All right, let's get into a real example and see how this team player idea can lead to some seriously bizarre results, where our best players suddenly look like they shouldn't even be on the field.
So back to our apartment. If we test each of these predictors one-on-one against the price, they look like absolute all-stars. Area, number of bedrooms, number of parking lots, they all have really low p-values. And in stats, a low p-value is fantastic. It means the relationship is almost certainly real, not just some random fluke. These are, without a doubt, significant lone wolf predictors. But now, just watch what happens when we put them all together on the same team in one big MLR model. First, look down at the bottom at the overall model score. That p-value of 0.01 is great. It means the model as a whole is a really good predictor. But now, look at the individual players. Look at those p-values. Area has skyrocketed to 0.70. Parking lots is up at 0.11. All of a sudden, two of our star predictors look completely useless. What is going on?
And this is it. This is the paradox we're talking about. We've built a model that works, but it seems to be filled with predictors that have no power on their own. The cause is a super common, but also super tricky issue that pops up in data all the time.
Okay, to solve this mystery, we have to become data detectives. See, the problem isn't with our predictors themselves. It's with the hidden relationships between them. So let's grab our toolkit and start investigating. Our prime suspect has a name, collinearity. This is what happens when your predictors aren't really independent. They're correlated with each other, telling the model pretty much the same story, and they end up just stepping on each other's toes.
And really, it's just common sense, right? An apartment with a ton of square footage is almost certainly going to have more bedrooms. So when you put both of them into a model, how is the model supposed to know who gets the credit for the higher price? They're fighting over the same piece of information.
This path diagram shows us exactly how that overlap works. A predictor's total effect, its lone wolf power, is actually made up of two things: its direct, unique impact, and an indirect effect that travels through the other variables it's correlated with. When predictors are tangled up like this, they end up sharing their explanatory power.
So how can we actually measure this overlap? Well, we use a pretty clever tool called the variance inflation factor, or VIF. It basically runs a little regression between your predictors to see how much they explain each other.
So for example, if the other predictors in your model can explain 90% of the movement in just one of your predictors, that variable's VIF score would be 10. A high VIF means it has very little unique, new information to add to the conversation, which makes it incredibly hard for the model to pin down its true, individual effect.
All right, let's see this in action. We'll compare our confusing apartment model to a totally different model where the predictors actually work together beautifully, even though they're still a little bit correlated.
Okay, check out this model. It's predicting a student's GPA based on their entrance and interview scores. Now, these two scores are definitely related, but look at their VIF scores on the right, just 1.41. That's super low. This is what we'd call a healthy level of correlation, and because of that, both predictors stay strong, significant team players with fantastic p-values.
Now let's go back to our troublesome apartment model. And what's so wild here is that the VIF scores aren't even that high. They're pretty low, actually. Yet even this mild level of collinearity was enough to make the unique contributions of area and parking lots basically disappear statistically, turning their p-values from great to totally insignificant.
So this brings us to the most important question. What are you supposed to do when you think your predictors might be conspiring against you? How do you build a model that you can actually trust? First, you got to know the warning signs. The biggest red flag is exactly what we saw, a great overall model that's packed with seemingly useless predictors. You should also watch out for coefficients that just flip-flop all over the place when you add or remove other variables. That's a classic sign of trouble.
And once you've spotted the problem, here are some clear, actionable things you can do. You can simplify the model. Just take out one of the redundant variables. Or you can get a little creative and combine them, like creating a new feature that captures both area and bedrooms in a single variable.
Ultimately, the predictors paradox teaches us a really vital lesson. You see, great analysis isn't just about grabbing more and more data. It's about taking the time to understand the complex conversation that's happening inside your data, because that's where the real story and often the most surprising insights are waiting to be told.